what we had discussed earlier, the last topic was definition of this elliptic curve over any given field L, specific L, right? So this is the definition. It includes a point at infinity and any x comma y over a field of L cross L values in the specific format. Y square should be there plus any other terms should be equal to x cube and some other terms. It's a cubical curve, right? So why it is like that? It is because I have to have three roots for my equation, right? So equation should be satisfied at three different points, such a way that whenever I have 2 points, I should be able to solve them with the given equation to get the third point. This is our objective. Also, we included a point at infinity. I justified that using this diagram, right? Whenever I draw a vertical line, it is going to cut my given curve at only 2 points. But my basic rule says that I have to have 3 points. So the third point must be at infinity, right? Such that it satisfies the condition. This is one justification for the point that why we need a point at infinity. Okay, but I have another justification coming, but that's after another discussion. Okay, so I'll directly move on to the say next point. This I bring the abelian group into picture. Okay, so I want to see that the points on the curve, that is points on this elliptical curve, should form an abelian group. Okay, this is very important. It should be an abelian group. So what is an abelian group? If you remember, if let's say that let the 2 points P and Q, right, are on the given curve. We know that this particular elliptic curve is denoted by E of something, right? I will call this is FP, prime number, field of prime number, let's assume, right? Forms say an abelian group. Right, it's not always all the points present on the EC which we consider is going to form an abelian group only under one condition. Do you remember what is the condition? Right, this is if and only if the P plus Q operation, if you do, right, the result whatever you get after P plus Q, right, is also on the curve. Okay, is also on the same E of FP, right? So let's denote the P plus Q as a R. Now I have to understand that. Let's just quickly define the rules to be followed by every point that is present on the abelian group. Okay, so this implies we had P earlier, Q also already present on my curve, and R now, which is a new point, okay, on this E of FP, right, must satisfy the following rules, right? So these are from basic set theory. I'm trying to write them directly over here. So first rule is the simplest one, that is called as commutativity. So which means you have P plus Q also same as Q plus P, straightforward. With the commutativity we always have associativity. So this refers to, let's perform P plus Q first, then I add R to this, should also be same as P plus Q plus R. And the second basic rule of the abelian group satisfying the relationship. Then we have identity element, right? Existence of what is called as identity element. So I'm going to call that in this case as O. Okay, P is my point. P plus that identity element should be equal to the identity element plus the point P, which is same as P, right? I'll prove this particular concept as related to this elliptical curve later. Okay, but let's see that there should be a identity element, and I think you had asked me a question about O as infinity, right? So we will answer that with this concept. Okay, so infinity will be your identity element so that you get your P back. When you add a P to that infinity, you will get back the same point. We'll prove that when we solve some problems later. Okay, then we have the next thing coming up. This is called as inverse. Whenever there is an identity, there has to be an inverse. Okay, the inverse element that also should be present in this group. So this is something like inverse element is minus P. Okay, right. So I'll write inverse element minus P. This is such that I have a condition to satisfy. If you have minus P plus P, right, that's also equal to P plus this minus P, same should be equal to your identity element. So all these conditions must be satisfied by each and every point that is present on the elliptic curve, so that we can say that yes, each and every point on the curve is right going to be it's each and every point form a abelian group altogether. Okay, right. Now let's go ahead quickly. I'll come back to this when we solve the problems, and I justify all these points when we discuss further. Okay, so we can see that the first operation we see here is an addition. So P plus Q I did, but what is the exact meaning of that P plus Q in a group, in an abelian group? We need to investigate. Okay, so this is the so I lead to the this leads to the next topic, which has a direct link between, right? So the next one I'm going to do is addition. Okay, addition of points on the EC, right? I'm going to call it as uh, affine points. I think the textbook uses the same word, right? Affine points. So no, I referred many books. Maybe I don't have a hard copy of the Williams this thing with me, Stalin with me. No issue, no issues. I think I'm referring the concepts are basically derived from the same, right? If you have any difference between the William Stallings and what I discussed, please let me know. I can re-verify and I can continue. All right. Okay. So now let us consider a specific curve, right? I'm going to talk about addition of any 2 points on the curve. So P plus Q means what? We will try to understand now. Okay. So okay. All right. Now let us consider a curve such as okay. Let's say this is a curve, and let me take 2 points on this curve. Okay, and let's say the first point is over here somewhere. This is the point. I denote this as P x1 comma y1, and let me say I have another point over here. Let me call this is Q. Okay, this is other coordinate, so I have to give x2 comma y2. Now as per this rule, right, whenever I add the two uh, points, I should get a third point, but that addition does not mean a simple addition. Okay, why will I'll justify this later. So first let me draw it, the meaning of this. So by drawing a line, I know that, right, there has to be a line passing through these 2 points, right? And once you draw that like this, maybe, okay, let me slightly move this so that it overlaps. All right. So now I see that this is actually touching another point, right? This point is not we are actually talking about. The third point is not actually this, right? I'll come to the answer why later. Okay, let's denote this point as x3 comma y3. This point will give a name later. Okay, but the third point which actually says that this is the third point p plus q is actually on the other side. This point will be our r. Okay, that is x3 comma minus y3. So my intention here is, in order to calculate the third point r that is present on this curve, satisfying the conditions of abelian group, is nothing but you had x1 y1 x2 y2, two points. Okay, calculate the third point x3 y3 and change y3 to minus y3. That's all. I'm still calculating x3 y3 only, but just changing the y3 to minus y3. That is going to give me the third point. Okay, but how do I solve? I know this method already. We have done this, right? I need to find out the equation of this line, right? Y is equal to some mx plus c is there, correct? This line. So calculate the equation of that line, put the equation and solve simultaneously with the uh, given curve, that is the red colored curve. Solve them simultaneously to get the third root, correct? Yes, so let's do that. So we get equations now. These equations you are going to use to solve the problems. All right. Okay. So I think since we didn't had this, you were not able to solve the actual problems. Okay. Right. So let's do this. Yeah, I need to find a slope. So there are two versions of this problem. The first thing is that the simplest one I'm solving now. I'm trying to solve. Okay, so I'll make an assumption. Let the x coordinates of both points are not equal. X1 is not equal to x2. I'm assuming in this case. So in the sense, right, it's not the same point. So P and Q are not the same point. They are different. Okay, so that is satisfied by this condition. If you put x1 is not equal to x2, right, I'll just write what is the meaning of this. P and Q are not same. When they are same, in the sense when I have only one point, right, I have a different approach. Okay, that's why. Now first I need to find slope, right? M. Let's find the slope of PQ. It's a line which is passing through both of them. So how do you find that? From analytical geometry, I can directly write using the, yes, 2 point method, right? So that is m is equal to the difference of the 2 points in terms of y coordinate divided by the x coordinate, correct? So I can write m is equal to, let me write y2 minus y1 divided by x2 minus x1. So this is going to imply that I can actually convert this into my equation. That is, if y2 should be equal to slope m into, let me write x2 minus x1, right, plus y1. Okay, I cross multiplied and move y1 to other side. This is this form of equation. Now let me say that I know m now, because using the left hand side equation, m equal to y2 minus y1 by x2 minus x1, I should have calculated m with me, correct? Using that m, I can actually write an equation now, right? Instead of finding a y2, let me write y as my equation. So that means instead of y2, let me say I want to calculate a new point, right? See, what is my intention here? I want to find, go and find this y3. So y3 can be found, right, straightforward by using this. That is, I can simply write that this implies y3 is equal to, how do you calculate? M into, I need to calculate the x3 first. Anyway, this is the equation, that's all. I don't know the x3 yet. X3 minus x1 plus the y1. Only I changed x2 y2 into x3 y3 because they are also on the same line, right? So this is the equation of that straight line. All right. Now, once you have the equation of the straight line, we already have applied this. We solved this equation with the given equation of the elliptic curve, right? So that means I can quickly write the third point, right? On this line, on the straight line, intersecting the curve. What's the curve equation? If you remember, this has to be y square is equal to x cube plus ax plus b, right? So how do you solve? You simultaneously you can solve. Y square is equal to, so left hand side is y square. That y square I am writing the equation of the straight line, correct? So just now we wrote that is m into x3 minus x1 plus y1. This was a mx plus c format. I need to square this, correct? Because the left hand side is a square. Should be equal to, right, the same thing. X becomes x3 cube because x coordinate of my point is x3, correct? Plus it is a times x3 plus b. All right, so now if you simplify, I'm going to skip the step here, okay, because this is the same procedure. I just have to apply a plus b whole square on the left side and bring the terms to the left side, okay. So that means I'll simply write uh, I'm going to get this, right? You solve by yourself. If you get it doubt, please let me know. I can actually show the steps here, okay, but just to save some time, I'll skip this now as of now. So x3 cube minus, I'm going to get m square x3 square and few other terms equal to 0. Right. You know now that we are actually interested in only this term. Correct? Because I know the two roots. What are the two roots? One is x1. Other one is x2. Correct? And the third one is this x3. Should be equal to minus of this term, right? So that is minus of minus m square, isn't it? So this means what now? This means I can calculate the third point x3 directly by using m square minus x1 plus x2, because you know x1 and x2 already 2 points on the curve, right? We know the slope of the line using which we can calculate the x3. So once you have this x3, go back, put the x3 over here. We know m, we know x1, we know y1. You get the y3. So once you have the y3, change y3 to minus y3. That's all. You go to the other side of the x-axis, right? So that I reach r. Okay, that's a very simple, straightforward method. So let me write that point in a single sentence. This means anyway, I got the x3. This implies I write y3. Y3 is equal to, same thing. You can apply here. This is m into, this is x3 minus x1 plus y1. This is the equation which we have written already. So using this, I'm going to get r, which is x3 comma minus y3 is the required point, right? This is the point that is corresponding to p plus q of the curve. This operation is called as addition. Any 2 point you take on the curve, you add, you get the third point, that is r, using this technique. There is another very important operation. This is called as doubling of an operation. Okay. The second very important operation that we can do on the on this affine points. Okay. So that is, I quickly write. This operation is called as doubling of affine points. So once again, I will start from my equation. Y square is equal to, this is x cube plus a into x plus b. Okay, but in this case, I'm going to consider a slightly different view of the curve. Okay, so let that be, this is y, this is x, and let the curve be like this. Okay, it's one and same, wherever you want you can write, but okay. So let me consider a point, say here. See, this is the other point, other version which I was looking for earlier, where you are not able to draw the straight line passing through 2 points, wherein we can say that the p and q are same. I'm not able to draw two through 2 points. Let me show you. Let me draw the line now. If the line is going to pass through only one point, in that case it becomes a tangent. Correct? Now you see, this is the point which is say P. This is P. Now, if you do, there is no Q now. So Q is also P only, right? Now the other point has to be called as 2P. So it's doubling. That's why the name doubling comes into picture. But it's not 2P, it's actually minus 2P, and on the other side you get the 2P. Like the same concept just now we did, right? This will be the 2P. So since the y coordinate is negative of this, you call it as a minus 2P. Okay, so the minus 2P is on the that side, right? When you go to the other side, you get the 2P. Okay, all right. So that's the concept. No, that's a notation. That's all. It's like you see I think I missed the writing the name over here. So this case you see here, whatever the name you give to this point, which is x3 comma y3, this is actually minus r. Reflection. Yes. So what when you on the same side, whatever you get is actually the reflection of the actual point that is present on the other side. That's why the name is minus. Yeah, so now you see in our case we have minus 2p present here on the same side of p, other side will be the 2p. Okay, so that's why. Okay, now let's look at the mathematical version of this. What happens and how do you calculate the 2p exactly? Okay, we cannot do that by simple multiplication by 2. Okay, so let's start with this. Let's assume that the p and q are same like this. Okay, so this implies the line becomes, sorry, becomes tangent, right? So as soon as this becomes tangent, what is our approach to find the tangent in analytical geometry? It's simply differentiation. Correct? So I call the given equation as 1. So let's differentiate. This is differentiate equation number 1. So normally this is with respect to x, right? At that point P. This is important. So what happens? I think I have the equation as y squared. So y squared becomes differentiation 2y into dy by dx should be equal to x cube becomes 3x square plus a. Okay, right. Now this means in order to find the slope, right, of the tangent, I need m. That is nothing but simply dy by dx at the given point, right? At the given point in the sense x1 comma y1. That is p. Point p is, I'll write here, x1 comma y1. So this implies you keep only dy by dx on one side, take everything to other side. This becomes 3x square plus a divided by 2y at the point P. So m becomes equal to 3 times x1 square plus a divided by 2 times y1. So this is the slope I want now. Okay. Now using this I have to find out the other coordinates, right? So which means now you see that I got a slope m. Now I can apply this to get the equation, right? Directly I can apply this and get the equation using the same concept which we have used earlier. All right. Now I'll club these two together, right? Two concepts we discussed together as a formula, so that you can apply this formula to any problem that arises. All right. So I'll write, in short, this is the summary. Okay. So if let us say that we have 2 points p x1 comma y1 and q x2 comma y2, right, are on this EC, right? Then in order to find R is equal to P plus Q, I have to find out, let me call that as a variable, let me define that as a lambda. Lambda is equal to, so first case you see we calculated, it's like M, all right, it's just a M. So y2 minus y1 divided by x2 minus x1. This is when the x1 is not equal to x2, previous case. But the present case is 3 times x1 squared plus a divided by 2 times y1. This is when x1 is equal to x2. Same point. I have to calculate this lambda first. Once you have this, now I can use these lambda to calculate the x3 y3. That equation does not change. x3 is equal to simply lambda square minus x1 minus x2. And the y3 can be calculated using lambda into x3 minus x1 plus y1. So use these to get r x3 comma y3. This actually is minus r, but anyway I understand. Take the change the y3 to minus y3 to get this. So I'll write r as the term containing minus y3. Okay, so this is the p plus q if the 2 points are different, and this will be 2p, right, if the points p and q are same. Okay, all right. No, lambda is using this equation. You see here, this is lambda. Lambda square in the equation. Okay, I'll just go back. Just a second. So I think we called it as m. M itself is a lambda. Okay, I think I changed the notation just for that. So x3 is equal to lambda squared minus x1 minus x2 comes from this. Okay, so please let's note there this lambda equal to m. The same. It's a slope. That's all. Okay. Now there is another very important concept. So we understood the how do you do the addition and the doubling concept, etc. Right. But when it comes to the EC, we actually have discussed one point initially, saying that in order to apply this to the cryptography, right, we have to have a condition that it should be non-singular. Remember, non-singular refers to all the roots of the equation being, right, unique. They have to be different. Unique. They have to be. They should not be same roots repeating. In the sense, only when you have three different roots, right? I get this situation, right? See, this is root number 1. This is second root. This is third root. Are you okay? So consider first root is p, second root is q, and third root of this equation is minus r. Correct? Only when you have three different roots, I get this situation. If you have a curve which does not satisfy this condition, if you have, say, two roots are same, let me assume, okay, two of the roots are same, then I'm calling that particular situation as singular. The equation of your elliptic curve is a singular curve. Singular refers to either one sorry, either two or all the roots are same. Okay, there are some curves, because we know that elliptic curves can be derived from the natural numbers, right, real numbers, complex numbers, anything can be used to get the EC. But to be specific, to be for a given EC to be specifically used in cryptography, we want a condition. This must be satisfied, that the curve must be non-singular. Non-singular refers to all the roots are unique, they are different, there is no repeated roots. Okay, this is the must have condition. So before understanding what happens and why so, we look at the condition called singularity. What happens with the singularity and why it is very important, we'll see now. So theoretically, I simply explain what happens if you have singular case. Correct. But mathematically, we need to explain this and understand this, so that we directly jump into the concepts of cryptography. Okay. So this will be the last of mathematically, but next directly we are jumping into the concepts of cryptography itself. All right. So this is singularity. So the concept of singularity with respect to EC we are talking. Okay, so let's start with the notation. Let's try to write the notation for the EC as y square is a function of x. Let me denote in this way. Okay, now uh, this implies, right, let me take the f of x to the left hand side, so that I'm going to get a function like this. Okay, so this implies I can call it as a function of x comma y, that is equal to y square minus f of x. Are you okay? I take f of x to the left side, and that whole thing, whatever I'm going to get, I'll call it as a f of x comma y. The function has two variables. Now let me hold on to this. As of now, let me define singularity in terms of mathematics. Under what condition, right, in an analytical geometrical equation, right, you get a singular curve. For singular curve, this is the condition. Okay, for singularity of a curve, you have some curve that is f. If you perform df by dx, which becomes equal to df by dy, and both being equal to 0, right? If at all you get this condition, this implies you have repeated roots, right? This is the condition. Now we have an equation f with us, that is represented by equation number 1. Let us try to perform the differentiation to get a condition. Okay, so this means let's do the df by dy, that is equal to, in the given equation, that is equation number 1, right? Okay, let me make let me make it more clear. Repeated roots at a specific point x naught comma y naught. Let me write it in this way. In the sense, if you simply differentiate, you don't get, right. You have to put a values of x and y at a given point x and y. X and y could, x naught y naught could be 1 comma 3, right? 1 comma minus 1, like that. I have to put a value, and if there the df by dx and df by dy become equal to 0, then it means, okay, at that point you have a repeated root. Okay, all right. Now I'm doing the same thing. First I differentiate the given function and put y naught over there. So df by dy is actually 2y at y naught, because y naught has to be substituted at some point. I have to calculate this. This is now becomes equal to 2y naught. Also, let's do the df by dx as per the condition that needs to be satisfied. So there is f of x is negative, so this is minus of f dash of x. Some differentiation happens. Okay. Now, again at x naught, this becomes minus f dash of a given point x naught. Okay. Now, what is the condition? Let's call these two equations all together equation number 2. Right. Now, the whole given equation is singular. Singular if the 2y0 becomes equal to minus of f dash of x naught, isn't it? Because it says that they have to be equal, not just this, should be equal to 0, then only. Okay, right. This means, now you see, I can write like this. This means if f dash of x naught is 0, this means f of x naught is also 0. That refers to, right, already I have written f dash of x naught, right? This is 0, right, is the condition. Other condition which is simpler, in order to calculate the two different differentiation and then getting to the answer, you find, you anyway you have a f of x, right? Put f of x naught, you get a 0 over there. Differentiate and put f x naught, that also becomes 0, means it is repeated roots. Okay, this is the other condition, right? So now minus of f dash of x naught is 0, right? That means what? That is 2y naught. 2y naught is equal to 0. This is 0 means this is 0, which means y naught is 0. So y naught is 0 means I can go back and I can put here, right? So see here, this whole term is equal to 0, which means, anyway, otherwise I'll make it more simple. I don't want to equate the whole thing to 0. Simply make this 0. Y naught is 0, right? Yeah, this function is 0, right? Means this has to be 0, right? Then only the whole equation will satisfy. So which means f of x naught is also 0. That's why I have written f of x naught is 0. This is already 0. The term which at the middle is already 0. Correct. So that's why I wrote, even if f of x naught becomes equal to 0, it means it is a double roots or repeated roots. Okay, so I understood that for a given curve, y square is equal to x cube plus ax plus b, right? If at all I find that f of x naught is 0 and f dash of x naught is 0, then that particular curve is said to be singular. Now, in the text books, we see that there is another condition. So the basic required condition is only this, but they use these equations to derive another condition in terms of a and b. What are the conditions on the terms a and b in your equation, so that the whole function becomes singular or non-singular? Okay, that's important with respect to the textbooks. Otherwise we don't need them as it is, but anyway, since they have done in almost all reference books where I have seen, they have given the condition, right? I think you might have seen a condition like 4a cube plus 27b square equal to 0 is a condition, right? So now I am going to show that how you get that. It's a smaller one, right? So let's quickly do that. So we start with uh, y square is equal to x cube plus ax plus b is the curve. So I just have seen that f of dash f of x and f dash of x should be equal and should be equal to 0 from the above condition. Just you can see above this. So first let us find the f of x. F of x is on the right hand side, correct? So let's write what is f of x. F of x is nothing but simply this is x cube plus ax plus b. Also calculate what is f dash of x. That should be 3x square plus a. Now according to the condition, right? What is the condition? Condition says I have to write f of x, equate it with f dash of x should be equal to 0. This is the condition for singularity. So let us substitute. Just now I calculated f of x is x cubed plus ax plus b. And on the right hand side I have f dash of x, that is 3x square plus a. This whole thing should be equal to 0. Okay, now what we can do, okay, use this to get the value of x square, right? Because since this function is 0, I can take a to the other side. This is minus a divided by 3. let me hold on to this. I'm going to use this somewhere else. And okay, I also have x cube plus ax plus b equal to 0. I multiply by that by another x. So this implies, see, x power 4. How you get x cube into x plus ax square. There is a ax, multiply by this, plus bx equals to 0. Okay. Now what I can do here, every x square is minus a by 3. So this is minus a by 3 whole square, correct? Plus a into minus a by 3 plus bx equal to 0. Are you okay? Okay. Now this becomes what? This is a square by 9 minus, I think this is a square by 3 plus bx is equal to 0. Correct? Uh, okay. Now let's calculate then what happens to the term. This is a square minus, this is 3a square whole divided by 9, correct, plus bx is equal to 0, right? So this is 1 minus 3 is, this is minus 2, right? Plus bx equal to 0. So let's calculate x in that case. So this becomes uh, 2a square divided by 9b. I got a value of this. Right now I think I got a x value, so that means I can put it over here. So anyway, so I implies 3 times x value I got. This is the location of x where the condition is satisfied, okay, in terms of a and b. So this is sorry, not 3, 2. So I write 2a square divided by 9b the whole square, because 3x square plus capital A is 0. Okay, now this means 3 into 4, I think a to the 4 divided by, this is 9, oh, sorry, not 9, 81. 81b square plus a is equal to 0. So let's try to simplify this further. 12a to the 4 plus 81 a into b square, correct, whole divided by 81 b square is equal to 0. Anyway, this is gone to the other side. A also I can cancel, correct? 1a can cancel with the cube. Then 12 and I think I can take out a 3. 3 is common, right? So this means when this is 4a cube plus 4 into 20, sorry, 3 into 27, right? Okay, 27. There is a b square is equal to 0, right? This is the condition for singularity, right? This is the singularity of the EC which we have considered. But we know now that we are specifically looking for 3 roots, right? So therefore, this is my final conclusion. Since, right, EC requires 3 unique roots, right? This implies the EC should be non-singular. If it is singular, roots are common. There are some roots which is located at the same point. I don't want. So it means it is non-singular. So what we apply for cryptography, the EC related to the cryptography is this. This means the required condition actually is 4 a cube plus 27 b square should not be equal to 0 is our condition. Okay, so equal to 0 is a condition for singularity which we don't want. Is it okay? Okay, now let's proceed further. In addition to this, right, we already have discussed that the addition is possible, p plus q to get a r. Then we have a p, you can convert the p into 2p. Doubling these operations. Using the two operations, we actually have a complicated operation in on the points present on the elliptic curve, so that we can apply this to the cryptography, and that is called as a scalar multiplication. This is also equally important, and we see instead of looking at a p converting p into 2p or p plus q, what we commonly see in the cryptography is this. Okay, scalar multiplication. And the scalar multiplication can be easily performed by extending the concepts which we have seen earlier. Okay, all right, so that is, let's write let me write one curve which is a standard polar curve, so that I can show exactly what is happening. Okay? This is x. Okay, let me write a curve. So just for, so some of the curves, standard curves, EC curves are actually having two different parts. Okay, like this also you get some curve. Okay, I just want to show you something, so for that reason I specifically require this shape. Okay, now let me say that I have a point P. Okay, so that point P is here. This is the point P. If I have just P, I can actually perform a scalar multiplication like this. What if you want to perform P plus P plus P so many times? P plus P plus P plus P dot dot dot. I want to do this maybe lambda times. So P plus P is 2P. P plus P plus P is 3P. So if you do that lambda times, what you get? You get lambda P. So you see that you are actually multiplying P by a scalar quantity, that is lambda. That's why this is called as, right, scalar multiplication. But what exactly happens on the curve is important. Take a what you call, let me draw the tangent through this point. Assume that it cuts the curve at another point. Correct? Just so to touch, right? But I'm not using that. I'm taking the opposite side. Correct? I'll go to this side. So this point is now. I'll just highlight the operation. Okay, this is where it is touching. The other side will be what? Will be 2p. Correct? So this point is now 2p. Okay, now how do you get a 3p is my question. You know p, you know 2p. How do you get 3p? What should be your approach? In the sense, you had a point p and you want to draw a tangent here, is it? You expect this, right? Maybe, but in that case I get a different point, say maybe q, right? Yeah, one more. I have to draw something more. That's right. But what what is that? So how do you get a 3p now? Basically, simple 3p is nothing but p plus p plus p, correct? Out of which I club the 2p, right? So I'll write here. So this is my idea. So I need 3p means p plus p plus p. Okay. These two p's, I get a 2p, right? Can you take 2p as q and p as p? So p plus q is nothing but draw a line through those 2 points, correct? Mm. Tangent. It's no more a tangent. It's actually it should pass through. I think I'll change the color. Uh, okay, so through P and 2P, I'll draw another line. Okay, like this. So you see that it's going to touch the curve over here, but I'm going to move to the other side. So this curve will be, this point is 3P, right? And 4P will be P plus 3P is 4P and so on. Now you should get some idea that why it's not a straightforward calculation from p to 2. Whenever this intersects on other side, why you are not calling that as the uh, required point? Like p, draw a tangent, you reach some other side, that is not going to be your 2p. Its image on the other side will be the 2p. Okay, this is because when you want to have a complex cryptographic technique, right, every time you have a special operation called changing the y coordinate, that makes it difficult for coming back, right? Only those who know the exact techniques are able to come back. Otherwise, right, it becomes too difficult. When you have lambda times repeated, you see lambda times you are changing your coordinates. You get a point, take the reverse of that. One time you get a 2p. Once again draw a line, take other point, change its coordinate, get 3p. Correct? This is repeating lambda times if you want to go for lambda p. Correct? Get a 4p, what you will do now? Once again, p and 3p connect, get another point. That's the other coordinate. That's not the other coordinate. Change the y value to the other side, right? No, no, this is just no. It's something like the idea here is just to add one more step to your calculation. That's all. This is no. Description is one more step, one more additional step. That's all. Those who know definitely can come back. No issues. Coming back is fine, right? Since I know the method now, I can definitely come back. But when you are doing some calculation here, it actually adds up one more step to that, right? So that's what is making things difficult, right? You are adding a extra step to that, something like you are adding one more step of security. That's all. Okay. True. Correct. Any point, yeah, you can change it as per the requirement and you will keep adding up more and more points, right? So how many times you, again, most of the time how many times you have done that also might not be known, like what lambda you have used, maybe I don't know. Correct. So how many times you have to do the decryption also is unknown to us, right? So that also is another added point for the security purpose. Okay, so these are the basic operations we have to use when it comes to the encryption using this technique. Okay, but now I want to begin the concept of encryption. There are, say, okay, no, I'll write the cryptography first. So if you look at the applications of the cryptographic techniques, we have two major applications. Okay, if you remember, the first could be the commonly known as encryption. Encryption, decryption are the same thing. My application is to achieve what is called as a secrecy. I just want to maintain some secrecy. I use the concept called encryption before sending, which means you have to do the reverse on the other side. That is decryption. Okay, that's one thing. Second one is that, yeah, I'll come to the diagram maybe in tomorrow's class. Okay, the encryption has something to be done. Okay, that we'll see. And on the other side, the other major application of the whole cryptography is for authentication, right? What do you mean by authentication? I authenticate something means I'm actually going to put a signature. This is the application, right? When I want to show you that I'm the person who is sending this mail, I use digital authentication, right? I add that to my mail, right? Which means I am the person who is sending. You will come to know on the other side when you receive that. Okay, but encryption is something like, it's not authentication. Code the message such a way that in the middle nobody should get, so even though somebody gets access to that, should not understand what is there. Yes, that's the cipher. In both the cases, we have the same cipher coming out as a after this cryptographical procedure, right? We call it as the same cipher, but the how do you differentiate technically, right? Technically, encryption and authentication are differentiated, right? By differentiated by. Do you have any idea why? How do you differentiate? Type of keys used. What type of key you use for encryption is different from what type of key you use for authentication, right? This itself is the base concept of our EC based cryptography, right? So when I use a elliptic curve, I say that I am going to use the elliptic curve for cryptography. We have to generate two keys. So definitely that's needed. And actually I try to differentiate that by using the two terms. These two terms will be what you call will be explained in detail maybe tomorrow. Okay, so first one is called as a public key. The right. Now one of the either user or the receiver will use either public key or private key, okay, to uh, for a given application. For example, now I'll just say what it is, but the diagram I'm going to write tomorrow. If you want to go for encryption, right? If I want to maintain secrecy in the communication, the sender will use public key and the receiver will use a private key for encryption concept. Secrecy maintenance means, right, public key on the sender side, receiver side will use a private key. If I reverse this, okay, the sender will use a private key and receiver will use a public key, means that is authentication. So it's very clear that for every application we need two keys. One is public, one is private. Okay, so how do you use that and how those keys can be derived from the EC elliptic curve generates the whole concept of the cryptography using EC. Okay, that's what is coming up tomorrow in the next class. Okay, all right. So I think there we'll be able to finish up, wind up with the whole concept. Okay, only 1 hour of content is left maximum.